We're now done with our discussion on the terminology and properties of a binary tree. And let's now talk about two more things before we move on to the next lecture. And the first one will be about the application of binary trees. And the first one here is so-called decision tree. And it itself is a proper binary tree. Now you can see why I need to talk about the terminology of what a proper binary tree is before I talk about this application, right? And don't forget about the property that we proved about a proper binary tree. And so this will be the tree used to express the decision-making process. And it's quite straightforward. Basically, the internal nodes and also the external nodes actually got different representation for the reality. One is about the decision point, and the other one is about the consequence of making the decision. You can definitely go over this example by yourself. It's rather straightforward, but I would like to suggest another similar application, more like a decision making, that might be more useful to you. Right? Let me point it out. So this is something called assurance cases, actually, which people in the safety critical or mission critical industry actually adopt a lot to really argue that their system or their product is really safe and fit for purpose. And you can definitely do some research if you like. It's optional. If you like, you can simply research on assurance cases. You can simply Google or just go to the library and search for articles. I do have one potential article you can actually read if you're interested about how to construct assurance cases using the tree structure. But very quickly, I don't want to go too deep into it. Just want to show you some flavor of how you can use the binary tree or general tree even. I think in the assurance cases, definitely you may have binary tree, but you can also have general tree as well. This is actually how you structure the arguments. So you can say I have some claim, and that claim can be split into different subclaims. And eventually at the leaf level, I want to provide evidences to say for this particular subclaim, I want to supply this evidence to support it. So eventually you want all the internal nodes being the claims to be supported by the evidences correspondingly in the leaf nodes. So that'll be the idea. Okay? So this part over here is simply just one example of assurance cases in the tree structure. And if you are interested reading about it, you can definitely go to this paper. It's optional, but at least you know the binary tree or general tree can actually be used to assure certain claims you want to make about your software products. That'll be the first application. The second application I'd like to talk about is also very useful. It's called the infix arithmetic expression. We talked about postfix notation earlier. Let's now talk about infix. And each internal node represents an operator, either unary or binary. And also external nodes actually talk about the operand, like a number. Okay, so this will be one example. Let me show you, illustrate to you right away. It's rather straightforward. So this will be some example tree. By the way, this particular tree happens to be proper, because you can see for every internal nodes over here, for example, this one, you got 2 nodes over here. And for this internal nodes over here, you also got 2 nodes over here. However, it's not necessarily the case always, because remember we said before, the operator can be unary. Let's see just one example, right? If I want to have, let's say, -3, maybe +4, how do I represent this particular infix arithmetic expression in a tree? In that case, it would be something like this. So we want to do a plus first. So that means the root should be a plus over here. And then we got the left, we got the right. The right-hand side is rather straightforward. It should be just 4. So this will be external nodes, just 4. And this part over here will be some unary operation of the negation or the minus operator. So this will be just the minus operator over here, and then that one there is simply has the internal nodes, external nodes 3 over here. Right? You can see this tree over here is not really proper. However, it's still a valid infix notation. Right? It's just that this part over here is actually unary operation as opposed to the subtraction that's binary. Right? Of course, I can use a different symbol, but you can just remember that this minus over here is a different minus than this. This is the binary subtraction, and this one is the unary negation that will change the sign of the number. And let's now see a little bit more. You can see for every internal nodes, it's simply just the operation, the operator, about what kind of numerical operation you want to perform. Right? So these are all the, including these two as well. Right? Let me just say a little bit more over here. You can think about this part over here is really a unary operation. Right? Whereas this part over here is really about some binary operation. I think I can box just better. So this will be a binary operation. Something like we're going to do a subtraction, and somehow you got something on the left, you got something on the right. And for the left, over here, we know that it's going to be some division. And for the right, we know that it's going to be some addition. And what about the leaves or external nodes? They will represent the actual values you can actually manipulate. For example, 3 and 4. And also 3, 1, 3, 9, 5, 2, 3, 7, 4, and 6. Of course, I just forgot. I got another internal nodes over here. All right. So that's as far as the application I would like to discuss. But you definitely have to know, is the binary tree necessarily proper? I already discussed it. It doesn't have to be, because, for example, if we use some unary operator. The next question will be a very natural follow-up. How exactly do we actually evaluate the infix arithmetic expression that's represented over here? How exactly do we do that? We don't even know what this expression really is. It's actually rather complicated. So that will be the topic for the next one. Let me just show you the bullet points, and then we can get ready for the next part. To evaluate the expression that's really encoded in the tree, certain traversal over the entire tree, it will be required. So that's something we can discuss the next part.